Today, we are embarking on an epic journey through the life and death of stars, one of the most profound and beautiful stories in the entire cosmos. We will unpack the complete logical evolutionary path of four extraordinary stellar objects: blue giants, red giants, white dwarfs, and neutron stars. These are not just random lights in the night sky, they are distinct stages in a universal cycle governed by gravity, nuclear fusion, and the fundamental rules of physics that shape every corner of outer space. For decades, NASA and astronomers around the world have studied these stellar bodies, mapping their transformations, and revealing that a star's entire life story is written the moment it is born, determined almost entirely by one single factor: its mass. Every choice, every change, every final fate of a star traces back to how much matter it gathered from the cosmic clouds that gave it life. Let us start at the very beginning, where all stars are born, the dark, dusty molecular clouds that float silently through the cosmos. A star's life begins in a nebula, a vast cloud of hydrogen, helium, and tiny dust particles spread across light years of space. Over millions of years, gravity pulls these clouds inward, compressing the gas and dust until the core becomes hot and dense enough to ignite nuclear fusion. When hydrogen fuses into helium at the core, a star is officially born, entering the longest and most stable phase of its life, the main sequence. This is where stars spend 90% of their existence, quietly converting hydrogen into helium and releasing the light and heat that we see from Earth. But not all main sequence stars are the same. The most massive stars, those with 10 to 100 times the mass of our Sun, blaze to life as blue giants. These stars are cosmic powerhouses, burning with a brilliant, intense blue light that cuts through the darkness of space. Their surface temperatures soar to 20,000 to 50,000 Kelvin, far hotter than our yellow Sun, and their luminosity is thousands of times greater. Because they have so much mass, their gravity crushes their cores with extreme force, making nuclear fusion run at a breakneck pace. Blue giants live fast and die young. Their entire lifespan lasts just a few million years, a blink of an eye compared to the 10 billion year life of our Sunday. They never slow down, never cool down, and never evolve into the gentle red giants that smaller stars become. Instead, they race through their fuel, fusing heavier and heavier elements until they reach a catastrophic end. On the opposite end of the stellar spectrum are the stars that will one day become red giants, stars with 0.5 to 8 times the mass of the Sun, including our own Sunday. These stars spend billions of years on the main sequence, burning hydrogen steadily and calmly. But every star runs out of fuel eventually. When a medium-mass star uses up the hydrogen in its core, the fusion process stops, and there is no longer outward pressure to balance the inward pull of gravity. The core begins to collapse inward, growing hotter and denser, while the outer layers of the star are pushed outward by the intense heat from the shrinking core. This is the moment a star transforms into a red giant. The star swells to an enormous size, hundreds of times larger than its original main sequence form, and its surface cools down, shifting from white or yellow to a deep glowing red. A red giant is a star in its old age, a swollen, gentle giant that fills its solar system with its vast atmosphere. Our Sun will become a red giant in about 5 billion years, growing so large that it will engulf the planets Mercury and Venus, and possibly even Earth. Even as a red giant, the star's core continues to change. The collapsing core becomes hot enough to start fusing helium into carbon and oxygen, a brief burst of energy called the helium flash that keeps the star stable for a few million more years. But this second act of fusion cannot last forever. Once the helium is gone, the star has no more fuel to burn, and its final transformation begins. Now, we reach the next stage of evolution for these medium-mass stars, the white dwarf. After the red giant phase ends, the star can no longer sustain fusion, and its outer layers drift away into space, forming a beautiful glowing cloud called a planetary nebula. This nebula spreads out over thousands of years, leaving behind only the star's hot, dense core. This core is a white dwarf, a small, Earth-sized, stellar remnant that is one of the densest objects in the universe. A white dwarf has no fusion happening inside it. It shines only because it retains the intense heat from its long life of fusion. It is held up not by fusion energy but by a quantum force called electron degeneracy pressure, which prevents gravity from crushing it further. There is a strict limit to how massive a white dwarf can be, known as the Chandrasekhar limit, 144 times the mass of the Sunday. Any remnant heavier than this cannot be supported by electron degeneracy pressure, and it will collapse into something even more extreme. White dwarfs cool slowly over trillions of years fading from bright white to dim black, becoming a cold black dwarf that no longer emits light. This is the peaceful, quiet end for all medium-mass stars, a gentle conclusion to a billions-year-long life. But for the most massive stars, the blue giants and supergiants, with more than 8 times the Sun's mass, the story ends in a far more violent and spectacular way. These stars never become red giants. They burn through their hydrogen, helium, carbon, and heavier elements at a furious rate, fusing elements all the way up to iron in their cores. Iron is a dead end for stellar fusion. It cannot release energy when fused, so the core suddenly stops producing outward pressure. In an instant, gravity takes over, and the core collapses inward at a quarter of the speed of light. This catastrophic collapse triggers a supernova explosion, one of the brightest and most powerful events in the universe. A supernova can outshine an entire galaxy for weeks, releasing more energy than our Sun will produce in its entire lifetime. The outer layers of the star are blasted into space, seeding the cosmos with heavy elements like gold, silver, and iron elements that make up planets, moons, and even life itself. After the supernova fades, what remains of the star's core depends on its mass. If the core is between 1.44 and 3 times the mass of the Sun, it collapses into a neutron star, the final and most extreme object in our evolutionary story. A neutron star is the densest, smallest, and most extreme stellar remnant in the known universe. It is just 10 to 20 kilometers in diameter, roughly the size of a city, but it contains 1.4 to 3 times the mass of the Sunday. A single teaspoon of neutron star material would weigh about 1 billion tons, as heavy as a mountain on Earth. The core collapse is so intense that electrons and protons are crushed together to form neutrons, and the star is held up by neutron degeneracy pressure, an even stronger quantum force than the one that supports white dwarfs. Neutron stars spin incredibly fast. Some rotate hundreds of times per second, and they emit powerful beams of radiation from their poles. When these beams sweep past Earth, we detect them as regular pulses, calling these objects pulsars. NASA's X-ray, telescopes, and radio observatories have studied neutron stars for decades, revealing their extreme physics and helping us understand the limits of matter in the universe. If the core of a massive star is heavier than 3 times the Sun's mass, it collapses even further into a black hole. But that is a story for another day. Today, we focus on the clear, unbroken logic that connects blue giants to supernovae, red giants to white dwarfs, and massive cores to neutron stars. The entire evolutionary chain of these 4 stellar objects follows one simple rule: mass controls everything. Low and medium mass stars follow the path of main sequence: red giant, planetary nebula, white dwarf. High mass stars follow the path of main sequence: blue giant, supergiant, supernova, neutron star, or black hole. There are no random detours, no unexpected twists. This is the fixed logical cycle that every star in the Milky Way and beyond follows. This evolution is not just a curiosity, it is the engine of the universe. Stars forge all the heavy elements that make up the world we live on, the air we breathe, and the atoms in our bodies. We are made of stardust, forged in the cores of giants and scattered by supernovae. Every time we look at a blue giant, a red giant, a white dwarf, or a neutron star, we are looking at a chapter in the cosmic story that created us. NASA's missions continue to unlock new details about this stellar evolution. The James Webb Space Telescope peers into distant nebulae to watch new stars being born. The Hubble Space Telescope captures stunning images of red giants and planetary nebulas. X-ray observatories detect the high-energy light of neutron stars and supernovae. Every observation confirms the same logical framework: stars are born, evolve, and die, based on their mass, creating the diverse cosmos we see today. This is the wonder of astrophysics, taking the vast, seemingly chaotic universe and finding the simple, beautiful rules that govern it all. The stars are not just lights in the sky. They are storytellers, recounting the history of the universe, one fusion reaction, one collapse, one transformation at a time. Please like, comment, share, and subscribe to the channel.